thanks for having me. My name is Nathan, and I'm an undergraduate student researcher here at IQC under Professor Bradley Howard. And today I'm going to be talking about realizing pair coherent states for pair cat code using optomechanical systems. So as many of you may know, there's lots of challenges facing quantum computing today. There's things like decoherence. Quantum states are fragile, and they tend to decohere over time. There's the issue of scalability. We want to realize many qubit systems that can be valuable for quantum computations. As well, there's the issue of error correction, of which we're going to tackle in some codes. So there's many different systems for quantum computing. You may work on them yourself, whether it's trapped ions or superconducting circuits. But today we're going to be talking about optomechanical systems. So specifically, if we look at the diagram here, we can realize an optomechanical system by using a pumping laser and having two mirrors that are a distance apart, of which there's a cavity between. And if you allow one of the mirrors to move, you have this coupling between the frequencies of the photons in the cavity and the phonons by the moving. So this introduces some advantages from the mechanical system. We know that mechanical phonons can't propagate without a medium. So this allows them to have longer lifetimes and have error correcting codes. As well, we can make it so they have minimal crosstalk to the other modes in the system. So what does that system look like optomechanically? Well, we start with a single cavity mode, of which there is n number of photons in. And we start with the simplest version of our Hamiltonian with the creation annihilation operator for the photons, as well as our master equation describing that ideal state. Then we can add our mechanical mode. And similarly, we have the creation of the phonon and annihilation of the phonon operator added to our Hamiltonian. But of course, we want them to interact. So we have a coupling term that allows them to interact. And we see that interaction term get added to the Hamiltonian as well. But because we have a real state, there's going to be these effective baths representative of the environment. So we have the ability to lose phonons to the environment, as well as gain them. So you can see that with the addition of the gamma rate for phonons with the Lindblad operator, of the annihilation of our B phonon, as well as the addition or creation of the phonon rate in our master equation. Similarly, we have a cavity bath representing the environment. However, we want to have the thermal number close to zero. So we're just worried about a rate kappa of the photons dissipating from our mode. And you can see that represented in the master equation. So to understand the systems of optomechanical and quantum computing, we want to understand the basic quantum mechanics behind it. So starting with something like the ground state, if you displace the ground state, you have what's known as the coherent state. And we have a similar master equation here, where we have a single mode dissipation, and a similar Hamiltonian where we just have a single creation and annihilation, where the coherent state size is representative of this equation alpha. So a coherent state is a superposition of Fock states, as we can see from the top equation, that exhibits semi-classical behaviors of a harmonic oscillator. We can think of a coherent state like a harmonic oscillator if you took the ground state as the harmonic in its equilibrium and displaced it and allowed it to realize this oscillation. So using functions like the Wigner function, we can visualize different quantum states like the coherent state in this probabilistic realm. We know that because of the Heisenberg uncertainty principle, different quantum states are not exactly in a single spot. So we can see the relationship of this in the position momentum space with the Wigner function positive. And if we were to realize a coherent state optomechanically, all we would need is two frequency pumps kind of near our cavity, or resonant frequency of our cavity, that are spaced out by exactly the mechanical frequency. And this would allow us to realize the coherent state. So then how do we realize a cat state, and what are cat states? Well, they come from the idea of Schrödinger's cat itself. If we think about the coherent state as that pendulum, we think about the cat state as being both oscillations of the pendulum at once. This is the idea that we have a superposition of coherent states that are directly unphased with one another. And you can see what the even cat state look like in the Wigner function. So to realize this cat state optomechanically, we would have our pumping frequency be exactly 2 mechanical modes before the resonant frequency of the cavity. So how do we actually evolve this cat state from the ground state, and what does it look like mathematically? So as you can see by this probability distribution, and because of pumping at exactly 2 modes, we get the probability of our states going from exactly the ground state to these even Fock numbers as we allow the cat state to evolve over time. So we can see this related in our master equation by the A squared, or the number of phonons being displaced as exactly only come in pairs. This is true for the Hamiltonian as well, where we have the squared annihilation and squared creation operators. And this time as well, the size of our cat state is proportional to that alpha equation. So now that we've realized these cat states, how are they actually useful? Well, we can use these cat states to produce the positive and negative x axes of our block sphere, which is to realize a quantum state in general. And if we use the coherent states as our plus and minus z of the axes, we can actually realize the full block sphere through the superposition on y. So this allows us to realize different quantum states useful for quantum computing. But how do these help with the different error rates? Well, there's 2 main error rates we're worried about when we talk about quantum computing codes. There's the bit flip error rate and the phase flip error rate. So in order to actually determine which matters to us, which we want to reduce the most, we can take a look at what they're proportional to. In this case, they're both proportional to the size of our cat state, but the bit flip error rate is exponentially proportional. So if we increase our cat state size, we can exponentially reduce our bit flip rate and only linearly increase our phase flip error rate, of which we'll actually reduce using these pair coherent states. So if we go from the cat state, we know that we had a 2 modes, but for the pair coherent state, we still have 2 modes, but they're separate. So when you look at the Hamiltonian and master equation of the pair coherent state, you can see that there's A mode and B mode that are created and annihilated separately but at the same time. So the pair coherent state is that superposition of 2 coherent states as shown by the state equation. Now these pair coherent states have been realized in superconducting circuits, like you can see from this schema here in the literature for Gertler, where the size of these pair coherent states are determined by the gamma equation. So just like I talked about with the benefits of mechanical modes, the pair coherent states also improve your error correction. So how do we realize pair coherent states optomechanically? Well, similarly, we start with our cavity, because it's a real system, it's going to have a bath. We can start with our single mechanical mode as we did previously, and now we can add a second mechanical mode to realize our full equation of our full system for pair coherent states. Now we have quite a long master equation now, where we have the loss terms as we expected from each mechanical mode, as well as the loss terms associated with the cavity state. And now in our Hamiltonian, we also have the interaction of both mechanical modes and the cavity mode, as well as their individual terms, as well as the pumping and driving frequency terms. So this is the full system realized. And in order to realize a pair coherent state optomechanically, we would take a pump and we would at exactly 1 mechanical frequency A plus the mechanical frequency, B plus the mechanical frequency C away from our cavity resonation. And this would produce the pair coherent state. So we can actually eliminate, and one thing that I've worked on is eliminating the dependence on the cavity mode for our equations of this pair coherent state in our optomechanical system. And when you adiabatically eliminate this cavity mode, you end up with these equations here. Now I know it kind of looks like a mess. There's a lot of different terms and there's a lot of different rates. And there's a good thing to see actually as part of these equations, which is that the pair coherent state is still baked in. So when we take these terms, we can see that they look like the ideal pair coherent state as long as the other terms are small. So to optimize the system of equations to look like the ideal pair coherent state, we want to make sure that this f is much larger than 1, which is to say the rate of loss that that is similar to our ideal pair coherent state is much larger than the rate of all the other terms of the equation. So this is exactly what we do for parameter optimization. We want to take this real state and we want to make sure that the different coupling strengths of our modes and frequencies represent the ideal or a very large f. So this is exactly what I'm working on, which is coming up with this pair coherent state in an optomechanical system, and we hope to realize something that's similar to what's being done in superconducting circuits, which you can visualize using something like the joint Wigner function here. And we hope to get for both the adiabatically and full model a system that has a fidelity or is very close to the ideal state. So experimentally, how you could realize these pair coherent states and cat states using things like vacuum gap capacitors, and you could choose which type. There's two that you could think of, which is separating the mechanical modes physically or having the mechanical modes on a single resonator. They both come with their positive and negatives. On the mechanical one, you actually get to tune them separately so you can have a full continuous parameter space, whereas on the two mechanical modes, you only have a specific ratio because you're limited by a single resonator. So thank you very much for my talk, listening to it. I hope that you can see the benefits of optomechanical quantum computing, and I'll be happy to take any questions.
Is there any question on that side? Yes, please.
So you have this kind of a mirror to go from the photons to the phonons in your first slide, right?
In the first slide?
Yeah.
Go all the way back. Read this one or the...
No, the first.
Yeah.
Yeah. So, like, I'm just trying to. So, if you get a photon that gets absorbed or whatever by the mirror, do you need like the mirror to physically move because of the momentum of the photon or something? Like.
Yeah. So in order to have like the phonons and their own frequency, you would actually have that second mirror be movable, and that's what's coupling the cavity with photons to the like resonator with phonons. But this is more like an example system that's a bit easier to display. So we realized something more like on the last couple slides with those vacuum gap capacitors resonating, where you either have like an LC circuit that acts as your cavity, and then your resonator, the mechanical thing, is actually what acts as your mechanical modes.
Okay, so you don't actually physically have a mirror.
No, it would be more like those vacuum resonators.
Okay.
And that's experimentally, so I'm not working on that. I'm doing theory and things of that nature.
Okay. Any other question for Nathan?
Could you actually tell us a little bit more about the vacuum gap resonator or
Yeah.
Yeah.
For sure. So we'll go all the way back to this. Okay. So we have on the left here a single resonator, and we have LC circuit that's attached to it that would act as our cavity. And you can induce the cavity coupled to this resonator, and this would be like the system I first explained with a single mechanical motor. But what you could do is do something like you see the two mechanical modes on a single resonator and actually have them be coupled on just one, and then you can realize that pair coherent state pattern.
Okay, so the two things would be in.
Yeah,
this
here,
system.
you can faintly see something like what that would look like on top of that whole chip. Yeah, you might want to look up two mechanical resonators on a single node or something. You run into the issue when you separate them out that you have to, it's more resource intensive, because now you have two resonators where you need the gap to still be manageable, and you need to tune them separately. So you might choose to go for one even though you're limited on your parameter space. Like you might have a ratio that's like 2.3 from B to C or something along that range.
Okay.